So my Enpm presentation video, a form of introduction. Autonomous Robotics is a hand-on robotic course focused on the design, integration, and implementation of autonomous robotic systems. Throughout the semester, we develop practice skills in robot kinematics, motion control, sensor integration, localization, navigation, and autonomous decision-making through a series of laboratory exercises and engineering projects. The course review, which was mentioned in every single class, was the see, think, act cycle, and is broken into these three areas in perception, localization, kinematics, and planning and navigation. The seeing is in the perception, the acting is in the localization and the kinematics, and the thinking is in the planning and the navigation of the robots. Next, we have the hardware list. This is the complete robot, as we can see. This is complete my robots, the one that attempted the grand challenge. And going on the next few slides, I'll be explaining each part and what each part entails and what it did. So first things first, we have the main chassis and the wheels. For this project, I used a bearing four-wheel drive mobile robot platform, which has four wheels, a platform, four motors, one battery pack, which holds five batteries. And if you see at the bottom right corner, you would see two encoders, two optical encoders, which were kept at front right and the back left, or it's the front left and the back right. Next, for kinematics, we have a H-bridge and we have an encoder. So these were used for two different things. So the H-bridge handled the speed of the robot and also handled the direction of the robot. So if you wanted the robot to move forward, you know, okay, all the wheels are moving forward. So you set all the wheels to true, which they're moving forward. Then if I wanted to move backward, it is the opposite of forward. That's in reverse. Then if I wanted to pivot left, you make the left wheels to move in reverse and let the right wheels would move forward, which gives the pivoting effect. And pivot right is the opposite of pivot left. Now next, for the optical encoders were used to measure the distance. So the optical encoders have perforations at the corners or around the circumference of it. So the perforations allow light to pass through, and in between there's a photosensor. So each time it changes from darkness to light, that is recorded as a tick. Using the number of ticks and using the number of revolutions number of ticks per revolution, I was able to get through the formula the amount of ticks for 1 meter, the amount of ticks for 1 inch. Next, we have localization. Localization, I used BN055 IMU integrated with an Arduino Nano to get every single orientation. So when I saw the BN05 IMU, I likened it to a mechanical governor from my undergrad and was more of like, oh, balancing is getting the pitch, the yaw, and the roll of like a plane. But in this case, it was an on-road autonomous robot, so it only needed the X, which was the swivel around its own axis. So next, we have perception, which is one of the most important parts of this project. For perception, I used a Pi camera Model B and an ultrasonic sensor. The Pi camera allowed me to see what the robot is seeing. Everything is from the view, so it can just view it. You can view it. For everything else that was needed for the project, which was HSV masking, which will allow the robots to differentiate color, and also every single thing with the bounding box, the centroid, was all done through the Pi camera. The ultrasonic sensor was used for sensing an obstacle in its place, any obstacle that is in front of it, and knowing when to stop. The ultrasonic sensor handled that. The ultrasonic sensor has four pins: the VCC, the trig, the echo, and the ground. The trig and echo handles the calculation. The trig sends a signal into the obstacle and it is sent back, so it receives the signal at the echo pin, and they use that to find the calculation of knowing, oh, the distance between the robot and the obstacle. So now in the following picture, we have this testing time for the sensor, for the ultrasonic sensor itself. During this class, we used the ultrasonic sensor to check the distance measurements away from the sensor itself. So one fun thing I did, I put my hand in front of the sensor and moved it back to see whether it would go up or go down or not read at all. This was a good opportunity for debugging. And with all of this, was able to get the measurements for each of the distances away from the robot, and this was the testing period for it. Now next we have the gripper. The gripper, which serves as like the hand of the robot. So it's more like, oh, how's it going to grab each of the blocks and take them to the construction zone? That was handled by the gripper. Now, the gripper was being powered by a builder servo motor, a 180 builder servo motor. Now, a problem with this was the PWM for my motor was annoying, to be honest. So the builder servo motor has a three is meant to have a 3.5, 5.5, and 7.5 for the closed, half open, and fully open duty cycles. But for some reason, mine did not have any of those. Like it stayed closed all through. So it took a lot of debugging from me and as generous as Dr. Mitchell was to help me with it, that we removed it, we disassembled it, and put a mark on the motor itself to see what was happening, and it was never consistent. So this was a good opportunity for a lot of debugging and understanding more about the robot's interface and how to fix it. So now the software is used. The softwares used for this project were Python, and the brain of the whole project was the Raspberry Pi. The three libraries imported during this whole project was OpenCV, Matplotlib, and NumPy. OpenCV dealt with all the computer vision, Matplotlib dealt with every plot I needed to take, and NumPy dealt with every single thing that needed an array, which was mainly also in the HSV masking. So now this is a video of me putting the wheels together, putting the wheels together and doing them very meticulously because a problem of putting the wheels together was that if you screw it in too tight, it would not be able to overcome the friction of the wheels that you've exerted. And also, in my case, because I had a problem with my house being rugged, so there were rugs around my house and I didn't have any bare floor. So putting the wheels too tight in were a big problem because the robots couldn't move. This was also a problem for the gripper because I put it in too tightly was the first point of debugging for finding the reason why my gripper stayed constantly in the closed position. Now next we have me installing the H bridge, putting the H bridge in, putting it through the switch, and a challenge I had here was actually on the soldering because I had to solder the switch like three different occasions because it either came off or was in partial contact with the other head. So it was staying in the constant on state. It never went off. Whether I put the kill switch off, I put the kill switch on, it stays on. And this was a problem when shutting down the Pi with sudo shutdown 0. This was a big problem because it would go straight into a frenzy and start driving no matter what because I didn't implement a game over script by this time. So now I'm going into the testing phase. This covers every single or most of the tests that I did while building the robots. Okay, so first things first, we tested the Pi camera itself, and this was in the assignments where we were meant to get the green light itself, like put a bounding circle around the green light and put the centroid there. So this was a good introduction into the HSV masking, and green was a real good pro because green is more distinct and cannot be differentiated with other colors. Next was the arrow detection, and this arrow detection was to know the direction of the arrow wherever it moves. For this arrow detection, I used Harris kernel detection and implementation under the OpenCV library. So I should know, hey, which part has the most kernels and know that, okay, that is where it's pointing to. Next, we have the gripper test. Well, this was the gripper and the ultrasonic sensors together. So the point of this was to see whether the gripper would actually close, because at this point, I was still trying to debug the 3.5, 5.5, and 7.5 PWMs not working. So this was a good one to get the gripper to work, close, and as you can see, it closed slowly, and then the distance is changed from 4.3 to 5.19, so it's getting its distance measurements and also closing. So now this is the encoder testing to cover a distance. I got number of ticks, and it covered 1 meter or 0.5 meters. And next, this was the encoder testing to drive to 90 degrees, so turn 90 degrees, pivot left 90 degrees. And this is the integration of both of them together in moving. Actually, I use the IMUs in this turn This was to draw the rectangle and have the rectangular trajectory plot for one of the assignments, which helped in getting the IMU ready, getting the IMU good, because the first time I did it, it tried going to the origin and did not get the natural state. So the IMU, I took the natural state and took everything from there. This is the track block. Track block. What I did was implemented it at O until when it sees the green block, it stops and it turns until the green block is at the center of the frame of the pie. So you move the green block and it keeps on moving. If it's out of frame, it turns left until it sees the block in question. So it's really good to help in detection and help his detection algorithm and understanding what is the difference. After track block, we have now next few slides covers the strategy that I use or that I plan to use at the Grand Challenge and implement in getting all the blocks into the construction zone. So we have a 10 by 10 feet arena with a starting zone of 2 by 2 feet and a construction zone of 4 by 4 feet. The challenge entailed that I pick the blocks from red, green, blue from a cluttered environment and run this cycle 3 times. The strategy that I had implemented was that the robots would go into the construction zone, then it would scan for the block, scan for the first block, which is the red block, take the red block and backtrack back to the construction zone using the heading from the IMU and the encoder distance sensors for the distance that was covered. Now, robot performance. Unfortunately, my robot was not able to complete the Grand Challenge. It violated one of the rules of the Grand Challenge, which was it should not touch the boundary. So in the first run, the robots went straight into the challenges faced. There were a lot of challenges in the implementation of this project. As mentioned, the first challenge was in the gripper. The gripper had a problem because it wasn't closing at 3.5, 5.5, or 7.5. It stayed closed, so it wasn't opening from its rest state at 3.5, 5.5, or 7.5. So if it was in the open state, it would go straight to close and would be exerting more torque than needed on the motor, which also caused a bit of slippage and a lot of twitching of the servo motor. The solution to that was going beyond the limits of the reinstated limits on the servo motor, which was 10 PWM. Oh, sorry, it's PWM of 10. And I found mine to be a PWM of 12.5 open and a PWM of 8.5 closed. And that's really worked, and I really appreciate. And also was also through Dr. Mitchell's mentorship that I was able to understand that that was the problem and how to fix it. So as for a conclusion, I would say I'm really appreciative for all the experience I gained because I was not able to use a Raspberry Pi before. I had never worked on any hardware. So this course taught me Python, taught me how to work on hardware, taught me a Raspberry Pi, gave me patience in different areas and when I needed a lot of patience because of the PWM and the gripper and also in the HSV masking. I would like to say thank you to Dr. Mitchell and thank you to my fellow setmates for the help, for the advice, for the mentorship. So Dr. Mitchell, thank you for answering every single question that I had and thank you for opening my eyes to a new horizon. Thank you for all the materials that you gave us to read, study more, and to pique our curiosity more deeper into the engineering field. I do not take it for granted, and I say I'm really grateful. So thank you very much. This has been David, and this has been my ENPM 701 experience. Thank you. Have a good